Hello and welcome to the Drone Builders Collective. Whether you are tightening your very first bolt or fine-tuning a custom carbon fiber frame, you have found your crew. Before we dive into the hangar today, make sure to hit that like and subscribe button on whatever platform you are listening on. That way, you never miss a lesson in building the ultimate flight machine. This is the podcast where we break down the high-flying world of aerospace engineering into pieces you can actually use on your workbench. Every single week, we dive deep into the art and science of making things fly. We will explore aerodynamic principles, aircraft design, and robotic functions. You don't need a fancy degree to build something incredible. You just need the drive to learn, create, and launch.
Welcome to Aerodynamics and Flight, Lesson 1, Forces and Motion. Every aircraft, from a small quadcopter to a wide-body airliner, lives in a constant negotiation with the air and with gravity. It does not stay up because it has enough lift in some vague, permanent sense. It stays aloft, climbs, turns, descends, and accelerates because the forces acting on it are changing in specific ways. The useful starting point is simple. 4 major forces shape ordinary aircraft flight. Lift is the aerodynamic force that acts generally upward relative to the aircraft's motion through the air. Weight is gravity pulling the aircraft toward Earth. Thrust is the forward push produced by the propulsion system. Drag is the aerodynamic resistance that acts opposite the aircraft's movement through the air. NASA and the FAA both use these 4 forces as the standard framework for explaining basic flight. In straight, level flight at constant speed, lift balances weight and thrust balances drag. But that balanced condition is only one special case. NASA +1. This segment explains what the 4 forces are, how they change, and how they work together to determine an aircraft's motion. It also introduces airspeed, density, altitude, and energy, the ideas that make the difference between an aircraft that merely flies and one that performs a useful mission. Flight is about net force. A force is a push or pull. When all the forces on an object balance, its motion does not have to stop. Instead, it continues at a constant speed in a constant direction. That point is worth emphasizing because it conflicts with everyday intuition. A car traveling steadily down a highway needs its engine to keep producing power, but it is not accelerating. The engine's forward force balances rolling resistance and aerodynamic drag. The car keeps moving because the net force is 0. An airplane in level cruise works the same way. It is not using lift to go up if it is holding altitude. It is generating enough lift to balance weight. It is not accelerating if its thrust exactly balances drag. It can travel hundreds of miles per hour in a straight line while its net force remains 0. In engineering terms, the net force is the sum of all forces acting on the aircraft. A net force produces acceleration. Here, acceleration means any change in velocity. Velocity includes both speed and direction. So an aircraft accelerates not only when it speeds up or slows down, but also when it turns. This leads to several practical rules. If thrust is greater than drag, the aircraft tends to speed up. If drag is greater than thrust, it tends to slow down. If lift is greater than weight, the aircraft tends to gain altitude or curve upward. If weight is greater than lift, it tends to lose altitude or curve downward. If the forces are unbalanced sideways, the aircraft turns or slides sideways. These statements are useful, but they are deliberately simplified. In real flight, the forces are not always perfectly vertical and horizontal. During a climb, for example, the aircraft is tilted upward relative to the horizon, and some of the lift may be directed slightly rearward. During a turn, the lift force tilts inward. The basic 4-force model still works, as long as we remember that force direction matters as much as force magnitude. Weight. Gravity's constant demand. Weight is the force created by gravity acting on the aircraft's mass. It points toward the center of Earth. In ordinary aviation discussions, this is treated as down, even though the precise direction changes slightly as the aircraft moves over Earth's curved surface. Weight includes much more than the empty airframe. It includes the fuselage, wings, tail, landing gear, engines, and systems, fuel or battery mass, crew and passengers, cargo and baggage, sensors, cameras, tools, and mission equipment. Any external stores, such as tanks, pods, or equipment mounted under the wings. An aircraft's weight is not always constant. A jet airliner becomes lighter throughout a flight as it burns fuel. A battery-powered drone does not lose much mass while flying, because the battery stays on board even as it discharges. A cargo aircraft may be substantially heavier on one mission than another. A military aircraft may change weight and balance as it releases fuel, stores, or payload. Weight also has a location. Engineers refer to the effective location where weight acts as the center of gravity, often shortened to CG. You can think of it as the point where the aircraft would balance if it were suspended. The actual mass is spread throughout the aircraft, but for many flight dynamics purposes, it is useful to represent the total gravitational force as acting through this one point. The position of the center of gravity matters enormously. If it is too far forward, the aircraft may require excessive tail force to keep its nose at the desired attitude. If it is too far aft, the aircraft may become less stable in pitch and harder to recover from a stall or other upset. Cargo loading, fuel management, passenger seating, and equipment placement all affect this balance. Weight is often described as the force an airplane has to overcome. That is true in level flight, where lift must match weight, but it can be misleading. An aircraft does not need to cancel gravity once and for all. Instead, it needs to continuously generate the right aerodynamic forces for its current flight condition. A glider illustrates this well. It has no engine thrust during normal gliding flight, yet it can fly for a long time. It is constantly descending through the air, converting altitude into forward motion. Gravity is not simply an enemy in that case. It is part of the energy source that keeps the glider moving fast enough to generate lift. Lift, the aerodynamic force that supports flight. Lift is the part of the aerodynamic force that acts perpendicular to the direction of the aircraft's motion through the surrounding air. In ordinary, upright flight, lift points mostly upward. It is generated when the aircraft moves through air and shapes or redirects that airflow. The wing is the primary lift-producing component on a conventional airplane, but it is not the only one. The horizontal tail, vertical tail, fuselage, engine nacelles, and even other surfaces can generate aerodynamic forces. On a helicopter, the rotating rotor provides most of the lift. On a multi-rotor drone, each propeller creates an upward thrust force that functions as lift for the vehicle as a whole. For a fixed-wing airplane, lift depends on several broad factors: how dense the air is, how fast the airplane moves through the air, how much wing area it has, the wing's shape, the wing's angle relative to the airflow, the condition of the wing surface, the use of devices such as flaps and slats. The relationship is often represented by the lift equation. You do not need to memorize or calculate this equation to understand its implications. The symbols simply organize the major influences. Is lift, pronounced rho? Is air density? Is airspeed through the air? Is wing area? Is the lift coefficient, a number that describes how effectively the wing is producing lift in its current shape and orientation. The key feature is the term. Lift rises roughly with the square of airspeed, all else equal. Double the airspeed, and the available aerodynamic force can increase by about 4 times. This is why aircraft need a takeoff roll. They must accelerate until the wings can create enough lift to support the aircraft's weight. It is also why a small increase in speed can have a major effect near takeoff or landing, and why excessive speed can create structural loads beyond what an aircraft was designed to withstand. Lift is often associated with the curved upper surface of a wing. Wing shape does matter, but a complete explanation has 2 closely connected parts. First, the wing creates a pressure distribution. Air pressure tends to be lower over portions of the wing and higher beneath it, creating a net upward force. Second, the wing turns air downward. If the aircraft gives the surrounding air a downward change in momentum, the air exerts an upward force on the aircraft in return. These are not competing explanations. The pressure field around the wing is the mechanism that turns the airflow. A useful mental picture is that the wing is continuously persuading a large mass of air to leave with a downward component of velocity. The resulting upward aerodynamic force is lift. Lift is not necessarily vertical. It is perpendicular to the relative wind. The direction of airflow is seen by the aircraft. In a bank turn, the aircraft's lift vector tilts. One component supports the aircraft against gravity. Another component pulls the aircraft toward the center of the turn. This is why turning requires more total lift than straight and level flight. Thrust, the force that sustains forward motion. Thrust is the force produced by a propulsion system to push or pull an aircraft forward. A propeller generates thrust by accelerating air backward. A jet engine generates thrust by taking in air, adding energy, and ejecting it rearward at higher speed. A rocket produces thrust by ejecting exhaust gases and does not need surrounding air to operate. The simplest way to understand thrust is through momentum. If an engine or propeller pushes mass backward, the aircraft experiences an equal and opposite push forward. That is a practical application of Newton's third law. Different propulsion systems produce thrust in different ways. A piston engine turns a propeller, and the propeller accelerates a large amount of air rearward. A turboprop uses a gas turbine to turn a propeller. A turbofan accelerates a large mass of air, much of it through the fan rather than the hot engine core. A turbojet accelerates a smaller mass of air by a larger amount. A rocket ejects high-speed exhaust and can operate in the near vacuum of space. A multi-rotor drone's propellers direct thrust mostly downward, and the vehicle tilts to create a horizontal component for forward movement. For a conventional airplane, thrust is usually shown as pointing forward, but its exact direction depends on engine placement and aircraft attitude. An engine mounted below a wing, for example, may have a thrust line that sits below the aircraft's center of gravity. Changing thrust can then create a pitching tendency as well as forward acceleration. Thrust is not the same as power, although the two are closely related. Thrust is a force. Power is the rate at which energy is delivered or used. A bicycle provides a familiar analogy. When you pedal, your legs produce power. The tires apply a force to the road. At low speed, the same power can produce a relatively large driving force. At high speed, the relationship changes. Aircraft have a similar distinction. Jet aircraft are often discussed in terms of available thrust. Propeller aircraft are often discussed in terms of available power. Both need enough propulsion capability to overcome drag, climb, accelerate, and operate safely under demanding conditions such as hot weather, high altitude, or maximum takeoff weight. An airplane does not need thrust merely to stay in the air. A glider can remain airborne while descending without engine thrust. What thrust primarily does is maintain or increase the aircraft's energy. It can compensate for drag, provide acceleration, and allow the aircraft to climb without trading away altitude. Drag, the price of moving through air. Drag is the aerodynamic force that resists motion through the air. In normal forward flight, it acts generally rearward, opposite the aircraft's direction of travel through the air mass. Drag is not caused by one thing. It is the total of several effects, and different effects dominate in different flight conditions. At a high level, drag can be divided into two broad categories. Parasite drag, which is associated with moving the aircraft's surfaces and body through air. Induced drag, which is associated with producing lift using a finite wing. Parasite drag includes skin friction drag, form drag, interference drag, and drag from exposed equipment. It generally rises quickly as speed increases. Skin friction drag comes from air rubbing and shearing along the aircraft's surfaces. Even a polished wing experiences it. A rough surface, bug contamination, ice, dirt, rivet heads, gaps, or poorly aligned panels can increase it. Form drag comes from airflow separating around shapes that are not streamlined. A blunt object leaves a disturbed, lower pressure wake behind it, and the resulting pressure difference pulls backward on the object. This is why a streamlined wheel fairing creates less drag than an exposed wheel, and why a sleek fuselage is more efficient than a boxy one. Interference drag occurs where flows meet and interact, such as at the wing fuselage junction, landing gear attachments, struts, antennas, or engine pylons. These junctions can create complicated local flow patterns that add drag. Induced drag is different. It exists because a real wing has tips. Air tends to curl around the tips from the higher pressure region below the wing toward the lower pressure region above it. This creates wingtip vortices, rotating tubes of air in the wake behind the aircraft. Those vortices represent energy that did not go into useful forward motion. They also cause downwash, meaning the air behind the wing is deflected downward. The wing's lift vector is therefore tilted slightly rearward, creating a drag component. Induced drag is highest when the aircraft needs a lot of lift at relatively low speed. This includes takeoff, initial climb, steep turns, slow approach, and gliding slowly. It becomes less important as speed rises, provided the aircraft does not need unusually high lift. Parasite drag behaves in the opposite general way. At low speed, it is relatively small. At high speed, it becomes increasingly important. This creates one of the central trade-offs in flight. Flying too slowly can create high induced drag, while flying too fast creates high parasite drag. At some speed in between, total drag is lowest. That condition is important because it is often associated with good glide efficiency and useful range or endurance performance. Different aircraft are optimized for different parts of this trade space. A glider prioritizes low drag and a high lift-to-drag ratio. A fighter may accept high drag in exchange for speed, maneuverability, and mission capability. A cargo aircraft may accept aerodynamic compromises to carry bulky payloads efficiently. Drag is not optional. It is the unavoidable cost of moving through air and generating lift. Aircraft design is largely the art of managing that cost. The balanced cruise condition. The classic image of flight is an aircraft cruising straight and level at constant speed. In that special condition, and the vertical forces balance, so the aircraft does not climb or descend. The forward and rearward forces balance, so it does not speed up or slow down. This does not mean the engines are idle or that nothing is happening. The engines are continuously producing thrust. The wings are continuously producing lift. The aircraft is continuously pushing air around, creating drag, and using fuel or electrical energy to sustain motion. It is better to think of cruise as an active balance, not a passive resting state. Consider an airliner at cruise altitude. Its engines are producing enough thrust to counter its drag. Its wings are generating enough lift to support its current weight. As fuel burns, the aircraft becomes lighter. To maintain the same altitude, it may need slightly less lift. The pilots or autopilot may adjust pitch, speed, altitude, or engine thrust. The flight is constantly being managed, even though it may look calm from the cabin. The idea that lift equals weight and thrust equals drag becomes misleading when applied outside steady, level flight. In a climb, descent, turn, or acceleration, the forces do not balance in the same simple pairs: climbing, descending, and accelerating. An aircraft climbs when its flight path has an upward component. This can happen in several ways, but the central requirement is that the aircraft must have enough energy to gain altitude. For a powered airplane, climbing normally requires excess thrust or excess power beyond what is needed merely to overcome drag. The aircraft can use that excess to gain altitude, gain speed, or some combination of both. Imagine an airplane in level cruise. The pilot increases engine thrust while holding the same attitude. At first, the airplane tends to accelerate because thrust exceeds drag. If the pilot then raises the nose slightly, the wing operates at a higher angle of attack and produces more lift. The aircraft begins to climb. Some of the extra engine energy is now being converted into gravitational potential energy, the energy associated with being higher above Earth. A steep climb and a fast climb are not necessarily the same thing. Climb angle describes how steeply the aircraft rises. It matters for clearing obstacles near an airport. Climb rate describes how quickly the aircraft gains altitude, often expressed in feet per minute. It matters for reaching a desired altitude efficiently. A small airplane departing a short runway with trees ahead may use a speed that provides the best climb angle. A jet climbing efficiently to cruise altitude may use a speed that provides a better climb rate or meets air traffic and engine operating requirements. Descent is the reverse energy management problem. An aircraft must lose altitude, speed, or both. It can reduce thrust, increase drag, lower the nose, or use some combination. A glider descends because it has no continuous engine thrust to offset drag. It converts altitude into forward motion. As it moves downward through the air mass, its wings generate lift and its body experiences drag. A well-designed glider descends slowly for each unit of forward distance traveled, because it has a high lift-to-drag ratio. A powered aircraft descending for landing may reduce thrust, lower the nose, extend speed brakes, lower landing gear, or deploy flaps. Each action changes the force balance and the aircraft's energy state. Landing gear and flaps can add substantial drag, allowing the aircraft to descend more steeply without gaining unwanted speed. Acceleration is more straightforward. Thrust must exceed drag, but the result depends on where the extra energy goes. If the pilot adds thrust and maintains altitude, the aircraft speeds up. If the pilot adds thrust and raises the nose, some of the available energy goes into climbing. If the pilot pulls up sharply without adding thrust, the aircraft may trade speed for altitude and eventually slow down. This is why pilots often describe aircraft control as energy management. Speed is kinetic energy, the energy of motion. Altitude is potential energy, the energy of position in Earth's gravity field. Engines add energy. Drag removes energy. The aircraft can exchange speed and altitude, but it cannot ignore the overall energy balance. FAA guidance describes this directly. When thrust exceeds drag, the aircraft's total mechanical energy increases. That energy may appear as greater airspeed, greater altitude, or both. Fa. Turning flight. Why an aircraft needs extra lift. Turning is where the 4-force model becomes especially useful. An airplane turns by banking, which tilts the lift force inward. Suppose an airplane rolls to the left. Its wings no longer produce lift directly upward. Instead, the lift vector points upward and left. The upward part of lift supports the airplane against weight. The sideways part pulls the airplane into a curved path. That inward pull is called centripetal force. It is not a separate mystery force created by the aircraft. It is simply the inward component of lift needed to bend the aircraft's path. The more steeply the airplane banks, the more its lift vector tilts sideways. That means less of the total lift is available to support weight. To maintain altitude in a turn, the airplane must generate more total lift. The pilot can do this by increasing angle of attack, increasing airspeed, or both. In many aircraft, The pilot also adds power because generating extra lift at a higher angle of attack increases drag. This has an important consequence. Stall speed rises in a level turn. The wing must produce more lift to support the same aircraft weight, and it may reach its maximum lift capability at a higher airspeed. A gentle turn produces a modest increase in load. A steep turn can impose substantially greater load on the aircraft's structure and on the occupants. This is why aircraft have maneuvering limits and why pilots are trained to manage speed, bank angle, and load factor carefully. From a passenger's perspective, a turn may feel like a sideways push into the seat. From the aircraft's perspective, it is a controlled redirection of lift. Airspeed is not ground speed. Aircraft care about how fast they move through the air, not how fast they move over the ground. This distinction is one of the most important in aviation. Imagine an aircraft flying through still air at 120 knots. Its airspeed is 120 knots, and its ground speed is also 120 knots. Now imagine the same aircraft flying into a 30-knot headwind. It still experiences airflow at 120 knots, so its wings create the same aerodynamic forces as before. But it now moves over the ground at only 90 knots. With a 30-knot tailwind, the opposite occurs. The aircraft still has 120 knots of airspeed, but its ground speed becomes 150 knots. The wing does not know or care how fast the landscape moves underneath. It responds to the air flowing around it. Lift, drag, stall behavior, and most control effectiveness depend mainly on airspeed and air density. Winds matter greatly for operations because they affect time, fuel use, takeoff and landing distance, navigation, and the aircraft's path over the ground, but they do not directly change the aerodynamic force associated with a given airspeed. This distinction can be especially unintuitive for drone operators. A small multirotor may hover relative to the ground in a wind, but it is not aerodynamically stationary. Its rotors and control system must generate a tilted thrust vector to resist the wind. The aircraft may have zero ground speed while still experiencing significant airflow. Air density, altitude, and weather. Air is not equally dense everywhere. Its density changes with altitude, temperature, pressure, and humidity. For basic aircraft performance, the two most important factors are altitude and temperature. At higher altitudes, the atmosphere is generally less dense. There are fewer air molecules in a given volume. Because wings and propellers interact with air molecules, less dense air reduces the aerodynamic force available at a given airspeed and configuration. Engines are affected too. Piston engines and gas turbines that rely on atmospheric oxygen generally produce less power or thrust in less dense air, unless they use systems designed to compensate. Propellers become less effective as the air thins. This means that high altitude can reduce both lift capability and propulsion capability. Temperature matters because warm air expands and becomes less dense. On a hot day, an airport behaves as though it were at a higher elevation than its physical location suggests. Aviation calls this density altitude. Density altitude is a performance concept. It describes how the aircraft feels the atmosphere. A hot, high-elevation airport can produce especially demanding conditions. The aircraft may need a longer takeoff roll, climb more slowly, and carry less payload or fuel than it could on a cool day at sea level. Humidity also slightly reduces air density, because water vapor is less dense than dry air. Its effect is usually smaller than the effects of temperature and pressure, but it is part of the complete picture. A pilot or operator does not need to solve atmospheric equations before every flight to understand the operational lesson. Hot, high, heavy, and humid conditions reduce performance margins. For example, a fully loaded aircraft departing a mountain airport on a hot afternoon must contend with reduced engine or propeller performance, reduced aerodynamic force at a given true airspeed, longer takeoff distance, reduced climb performance, obstacles and terrain that may demand strong climb capability. The same basic airplane, with the same engines and wings, may perform very differently at a cool, sea-level airport. Dynamic pressure. Why speed matters so much. A useful concept that connects airspeed and density is dynamic pressure. It is written as, dynamic pressure is not a separate force. It is a measure of the pressure-like effect associated with an airstream moving at a certain speed and density. It helps determine how much lift, drag, and control force the aircraft can generate. The equation contains the same two critical variables. Denser air increases dynamic pressure. Faster airflow increases dynamic pressure dramatically because speed is squared. If an aircraft doubles its airspeed while everything else stays the same, its dynamic pressure becomes 4 times as large. That does not mean every aspect of the aircraft's behavior changes by exactly 4 times, but it explains why speed strongly affects aerodynamic loads. At low airspeed, the controls may feel weak because there is not much airflow over the ailerons, elevator, and rudder. At high airspeed, small controlled deflections can create large forces and moments. That is why aircraft often have speed limits for extending flaps, landing gear, or other devices. The loads created by high dynamic pressure can exceed what those systems were built to handle. Dynamic pressure also helps explain why a small drone can be tossed around by a gust. Its low mass means even a modest aerodynamic force can produce a noticeable acceleration. A large transport aircraft experiences the same basic physics, but its greater mass and different control system give it different responses. Force, power, and energy. The terms force, power, and energy are often mixed together in casual conversation. In aerospace, keeping them separate makes many ideas easier to understand. Force is a push or pull. Lift, weight, thrust, and drag are forces. Work occurs when a force moves something through a distance. If thrust pushes an aircraft forward, the engine does work on the aircraft. Energy is the capacity to do work. Fuel contains chemical energy. A battery contains stored electrical energy. An aircraft moving fast has kinetic energy. An aircraft at high altitude has potential energy. Power is the rate at which energy is used or transferred. A more powerful engine can add energy to the aircraft more quickly, although the exact result depends on speed, altitude, and efficiency. An aircraft in level cruise uses propulsion power to replace energy removed by drag. An aircraft climbing uses additional power to gain altitude. An aircraft accelerating uses additional power to gain speed. An aircraft descending can reduce power because it is converting stored altitude into other forms of energy. This perspective helps explain why altitude is valuable. A high aircraft has options. It can glide farther if the engine fails. It can trade altitude for speed if needed. It may have more time to diagnose a problem, but altitude also comes with trade-offs, including thinner air, different engine performance, and possible pressurization requirements for crew and passengers. Aviation is full of controlled energy exchanges. Pulling up without adding power converts speed into altitude. Descending while maintaining speed may require reducing thrust or adding drag. Extending flaps can increase lift and drag, enabling a slower approach and steeper descent. A tailwind changes ground speed and trip time, but not the aerodynamic energy required for a given airspeed through the air mass. A headwind during landing can reduce ground speed at touchdown while preserving the airspeed needed for lift and control. The pilot, flight control system, or autonomous mission manager is continuously managing these exchanges. 3 practical flight scenarios. Consider 3 different aircraft to see how the same principles apply. A light airplane climbing after takeoff. A light airplane accelerates down the runway until its wings can produce enough lift to support its weight. The pilot then raises the nose slightly. The wing's angle of attack increases, producing more lift. The airplane leaves the runway and climbs. During this phase, the engine produces high thrust. Drag is also significant because the airplane is operating at relatively high lift and may have flaps extended. The airplane must maintain sufficient airspeed to avoid stall while also climbing steeply enough to clear obstacles. If the day is hot, the airport is high, and the aircraft is heavily loaded, the available performance margin may be much smaller. The airplane may still fly safely, but it may need more runway and climb less aggressively. A jet airliner in cruise. At cruise altitude, the airliner's wings generate lift equal to its current weight. The engines produce thrust equal to drag. The aircraft moves quickly through relatively thin air, where lower density reduces drag for a given true airspeed, but also requires careful management of speed and engine performance. As fuel burns, weight gradually decreases. The aircraft can often climb to a higher altitude later in the flight, because it is lighter. This is called a step climb. The goal is to find an altitude and speed combination that provides efficient operation while meeting air traffic, weather, and operational constraints. The aircraft is not coasting. Its engines are continuously replacing the energy removed by drag. A glider descending through calm air. A glider has no engine thrust during normal flight. It cannot maintain level flight forever, because drag continuously removes energy. Instead, it descends gradually, converting altitude into the forward motion needed to create lift. A high-performance glider can travel a long horizontal distance for each unit of altitude lost, because its drag is very low compared with the lift it produces. If it encounters rising air, called lift in soaring terminology, it can gain altitude and extend the flight. The glider makes the energy relationships especially visible. Altitude, speed, lift, drag, and weight are always interacting, even without an engine. What to carry forward? The 4 forces are not just a beginner's diagram. They are the framework that connects nearly every subject in aircraft engineering. Aerodynamics explains how wings and other surfaces create lift and drag. Propulsion explains how engines and propellers create thrust. Structures explain how the aircraft withstands weight, aerodynamic loads, maneuvering, turbulence, and landing. Flight dynamics and controls explain how force imbalances create motion and how pilots or computers manage that motion. Aircraft design brings all of those concerns together into one vehicle. For now, the essential ideas are these. Aircraft move according to the net forces acting on them. Lift balances weight only in a particular condition, such as steady, level flight. Thrust balances drag only when the aircraft is neither accelerating nor decelerating. Climbing, descending, turning, and accelerating all require a changed force balance. Airspeed, not ground speed, determines the aerodynamic forces that matter most to flight. Air density affects both aerodynamic performance and propulsion performance. Dynamic pressure explains why speed has such a powerful effect on lift, drag, and control forces. Flight is fundamentally an energy management problem. Engines add energy, drag removes it, and the aircraft exchanges speed and altitude as needed. The next segment, 1.2 Wings and Lift, Airflow, Pressure, and Momentum, builds on this foundation by examining how a wing actually produces the aerodynamic force that makes sustained fixed-wing flight possible.
And that brings us to the end of this episode of the Drone Builders Collective. Thank you so much for hanging out and building with us today. If you enjoyed this episode, please take a quick second to like, subscribe, and leave us a review on your favorite podcast app. Your reviews help other builders find our hangar and join the crew. Don't let the conversation stop here. Leave a comment on your favorite app or send us an email with suggestions for future episodes. Keep your batteries charged, your props balanced, and your mind curious. Until next time, clear skies and happy building.